So you can still see my slides, right?
Looks good.
Okay, cool. All right. So today's paper is Ocean Vista, which is a gossip-based distributed transaction system. So I took some of these slides from the author's original slides. So there might be like, I interleaved with some of mine to get into depth. So it might be not cohesive. So the research questions the authors are asking themselves is basically if it is possible to build a transaction processing system where conflicting transactions can be run in a strictly serializable order. Basically, what they're trying to achieve here is eliminating the write-write conflicts and sometimes read-write conflicts as well. And so that you could achieve sort of perfect strict serializability guarantees without aborting any transactions. The second thing they are trying to achieve is provide one round-trip time writes and also read data from a local copy only if with rights that are only acknowledged by a quorum. And they're asking if they can read from one nearby copy, not do like a WAN round trip, basically. So the intuition comes from a couple of cases in concurrency control where you do not need, like in transaction processing, where you don't need any concurrency control. So if you sort of imagine this axis on the Y as version numbers going from down, from the bottom to the top of the screen, and you have different events happening on these version numbers that you typically attach to transactions. So if your transaction is write only, then you don't have to, you basically don't need any concurrency control. You can just write them to different versions, and at the end of your highest version will be what your latest version, write is. On the other hand, if you just don't do any writes and you only do reads, then you could always get a version ID and a version timestamp and then retrieve the read corresponding to that. And you can achieve this by using a multi-version data store of some sort. What they're trying to do in this paper is have like build a transaction processing system where you have writes and writes that happen on one end and reads that happen on all like previous versions. And you can sort of draw a line in the between called a watermark where basically where your rights are visible to future transactions. And they are trying to achieve this by having a sort of an asynchronous protocol that just simply passes messages on like what they are, the states they are in, and in order to like move this visibility, version visibility forward, basically. So what the authors say, this Ocean Vista is basically, it's a multi-versioning transaction processing protocol that combines gossips and that basically combines a gossip protocol and in a way to provide a faster transaction. The reason why they want to use these watermarks are basically derived from like the three constituents or components of a transaction processing system: the transaction commit, concurrency control, and replication. All these three techniques, they all are based on something where they're all based on a concept where every replica tries to inform other replicas of something they have done. Like, for example, executing a transaction, now they have to notify somebody else. So they sort of achieve all this using this timestamps and by using this visibility watermarks, which are basically a pointer to a timestamp where the rights are of previous transactions are visible for future transactions. They sort of achieve these three with one single metric they call the watermark. See, the architecture of the Ocean Vista system looks like this. You have a bunch of data centers, DC 1 to 3 here in this example. And in each data center, you have a database servers. What each of these database servers do here is they perform three main functions. They participate in transaction coordination. So they accept client requests, coordinate with other database servers across DC and within DC to sort of commit this or abort the transaction. And what each database server has a multi-version storage for the shards that they are for the shard that they are basically replicating. And they also have to serve the third function of executing the transaction logic on the data and producing the output. And for each data center, there are a bunch of database servers. And there are also gossipers. So gossipers are special servers that coordinate within the data center, coordinate with DB servers within the data center, and they coordinate with gossipers across data centers. So essentially, this is referring to Alex's point earlier in the chat. It basically is to reduce communication between the data centers. What these gossipers do is they exchange the watermarks. We'll go into detail on how they compute and exchange it, but they exchange this watermarks to come into an agreement on what is the minimum valid watermark that they all, below which they can, the transactions are visible to future readers or writers, basically. So Ocean Vista proposes something called asynchronous concurrency control, which is a mechanism that their whole system is built on top of. And it has certain features that differentiates it from traditional systems. So here there are, like on the left, I have synchronous transaction processing, which would involve a sequential, which is the naive way you could process a transaction, not representative of like any high performance system though. So what you could do is basically you could read all the keys that you need for a particular transaction, compute what you compute according to the transaction logic, and then produce something called a write set. And what you could now do is write all the write set to their target keys, basically. However, what asynchronous concurrency control do is it basically sort of writes the transaction itself. So it does not compute the transaction, write the result, but the first step is basically it tries to replicate the transaction itself in order to simplify a lot of things like fault tolerance and stuff like that. So it writes the transaction, all this related logic across all the shards and across replicas of those shards. And once it succeeds in that, then it goes on to performing these reads and doing the compute. And finally, whatever comes out of these computation, it asynchronously writes them, and it asynchronously writes them and does not have to do it it does not need acknowledgement basically in this case, because it already has returned the transactions, the transaction logic itself. So whatever whatever failure may occur, it can just re-execute the transaction and deterministically, and then achieve the same output. So that is why they don't, for the third step, they just need asynchrony. They don't need it to be synchronous. And this is a very high level of how asynchronous concurrency control transaction works. Going on to an example, we have here two data centers. Left is, let's say, DC1, and the right is DC2. And you have three replicas ABC, or I would say shards, not replicas, shard A, shard B, and shard C. And then we have a client and a coordinator. So a client starts by sending a transaction to a coordinator. And what this coordinator does is it uses it generates a timestamp, a physical time using its local clock. And let's say this timestamp is 10. What it then does is it takes this transaction, does a write on all these shards that the transaction is touching. In this case, let's say it's all ABC. So it writes this version 10 with that transaction information to all the shards. And once it receives an acknowledgement from these shards, what it can then do is, then gossipers basically take over. And what this gossipers do is they sort of exchange the recent timestamp that have been this different data centers agree on. So for DC1, the gossiper might say that the server watermark is 12, for example, and it will convey this information to DC2. And in DC2 may also collect information from its replicas of shards A, B, and C on the right. And it will also come to a conclusion that the lowest watermark that can be visible from that data center is 12 as well. So finally, with this two information, what each one of the gossipers can conclude is that the visible watermark is 12, which means transaction with TS10 can be visible to, it can be made visible to outside. So what then happens here is the next step takes place, which is basically the read and compute step. What happens in this case is one of the replicas basically reads from other shards and then does a computation deterministically on what the output of the transaction should be, executes it, and then returns the reply to the coordinator, which replies to the client. At the same time, the coordinator also performs an asynchronous write to all the shards with the updated information. What essentially now happens is, in the first step on the top, when we did the write, what we did was we wrote the whole transaction itself. Now this transaction gets replaced by this value that we write in this asynchronous write step on the bottom. And that concludes basically the transaction, even though the client can be replied way earlier in the previous step itself. That you can, basically you can reduce a round trip time with that. So, okay, before I jump, here, basically what we have here is in the S, we have two phases, what they call two phases, the S phase and the E phase. In S phase, what we have is one round trip time communication. And what I observed is they basically compute the round trip time across data centers, not within data centers. I think they consider that to be a significant portion. So when you do the write, basically you incur one wide area RTT. And gossip usually also incurs one wide area RTT, but what they are claiming what they're claiming in the paper is that sometimes gossipers, you only need in order for you to reply to the client, you only need the other gossiper, for example, the DC2 gossiper, to send you an updated timestamp, which might happen concurrently. So there is no need for the DC1 gossiper to send. There is no need to wait actually for you to send to your watermark to from DC1 to DC2 and then wait for an acknowledgement, because DC2 has already notified DC1 that it wants its watermark is 12. So given this information, you could possibly skip that round trip time. So essentially, sometimes you only get one RTT latency. Otherwise, you would get two RTTs. Okay. So the performance of Ocean Vista comes basically from its ability to like batch transactions in an indirect way. For example, on the left, if you are doing transactions synchronously, you would have to do this one by one for each transaction and wait for the previous transaction to commit before doing the second one. But what ACC is able to do is you could just issue writes, because as I said in one of my previous slides that if you're just doing writes, they don't conflict at all. So at the end, the recent version becomes your recent write. So what you could do is you could basically issue all this write of the transactions for all this 100 transactions concurrently, and with the different timestamps, of course, and these timestamps have to be monotonically increasing. That's their requirement. But if all this can happen, then you can issue this writes concurrently, and gossipers can then exchange their watermarks in batch for all this write transaction, for all this 100 transaction. They can also be executed together, and the reply can be sent to multiple, like for all this 100 transactions at the same time. So this is sort of like an indirect batching under the hood. That gives it a better performance. So going deeper on how ACC works. So whenever there is a transaction, the coordinate procedure is kicked off. And what this coordinate procedure does is there is something called TID manager, which creates, that can be used to create timestamps. So what you get is a physical timestamp and some other replica information to make it unique and monotonically increasing. And the next step is in line 3 is basically you compute you extract the transactions write set, and for all keys in that write set, what you do is you issue a write request for all the shards where those keys are located. And you set the timestamp for that write to be TS and the value for that key to be the transaction itself. Before we go any further, let's look at what this write does. So what this write is basically is the replication protocol, where the coordinator basically issues tries to replicate the transaction across all the replicas, all the shards, and across replicas within each shard, basically. And to do that, it uses the fast packsource protocol or a variant of it. So essentially what it does is it sends a request with the key, timestamp, and the value to all the shards and replicas within the shards. Sorry, the key is tied to a shard. So all the replicas within a particular shard. And it waits for a superquorum. A superquorum is basically more than a majority, or you can imagine it as 2f+1 out of 3f+1 replicas. It's close to like 70% rather than the traditional majority, which is like the 51%. So once all these replicas, when each of these replicas get this request, they write it in their local MV data structure, MV storage, and they reply back to the coordinator. And the coordinator would wait for either a fast path or a slow path. So this a fast path is when 2f+1 out of 3f+1 replicas acknowledge by saying basically acknowledge to this request. Otherwise, if there are not enough replicas available, the coordinator would then issue a slow path message and wait for a final. It would basically send a finalize message, and it would wait for a finalized message from the replicas, basically. For the slow path, all we need is f+1 confirmations. But if you wanted to take the fast path, then we need more, as I said. Okay, going back. So once this write comes back, which means we have replicated the transaction on a majority of replicas for each key, then we check if any one of these write fails. And this is when we need to abort the transaction. What could happen is it could be possible that some of these writes succeeded, but some of these writes failed. And but no matter what happened, if one of these write even failed, then you need to abort the whole transaction. So which means you need to basically run another a consensus consensus ballot to ensure that these keys are marked as these timestamps are marked as aborted. I think this is one of the reasons. I read the chat before this presentation on why we need a fast access, and I think this abort is probably why you need fast access versus just using the regular Paxos. Because if you had a write happening, taking place, and then the coordinator then issues an abort because some other write failed, because as line 3 says, you could be you could have multiple writes in parallel for different keys, and even one of these writes fail, then you need to abort the transaction. So I think you need that fast access because that would introduce a conflict. The abort and the write would introduce a conflict, so you need a mechanism to recover from it. And that is why you need that larger quorum, essentially. So coming back to this abort protocol, what it does is it basically sends an abort with that key, with that timestamp, to all the replicas of all this, to all the shards. So for each shard, what these replicas do is they will apply, they will call abort on the MV storage, and then it will reply the success back to the coordinator. And the coordinator should wait for a majority of replies from each shard to ensure that this abort has been applied across a majority of replicas on each shard, basically, for fault tolerance. All right, so this all these steps coming back to line 6. Okay, if some write fails, then you need to abort it, and you need to return return from the procedure. Otherwise, what happens is the TID manager, you call the coordinator basically marks that timestamp in the TID manager, and this is used for calculating that watermark that gossipers exchange between different data centers. And after that, what happens is there is an asynchronous mechanism that checks if writes to all the replicas succeeded. And this is useful for, this is required in the future for read from one replica reads, basically. And this can only happen if the TID manager is able to confirm that all the replicas have replicated this transaction. Finally, in line 12, you wait for the results from all these writes, and then you basically wait for the execution results from the writes you made in 4, and then you return. Okay, so I was talking about MV storage that is being used for used by write and also the abort procedures. And what they essentially do is that what they are essentially is their operations on the multi-version storage in each of these replicas. There are 3 APIs for this storage. The first one is put, which basically maps the value to the key at that version. Gets that value at that version or the largest version that is less than the version you gave it. Abort basically removes that version, and it basically does not accept any other it basically does not accept the same timestamp again. Like for example, if you do a put after an abort, it won't accept for that version, basically. Okay, so, all right. And then going back here, we have this execute procedure where after you get acknowledgement from the gossip that you need to move the timestamps, now you need to execute this transaction and update the storage. For each transaction, for the timestamp, what you do is you extract the read set and then read all the keys with timestamp TS-1. So you read the previous timestamp version of for all the keys and put it into a temporary variable, like in this case, input. What this read does is it depends on whether you have fully replicated or not. If you have fully replicated, it's simple. You could just communicate with one of the replicas and then just get the latest version. However, if it's not fully replicated, you will know it because you would the coordinator, the replicas actually change the R watermark. And if it's not fully replicated, then you need like a quorum procedure again. So what this read procedure here does is it picks all the replicas that are holding this key, and then it issues a GET request to the MV storage and each of these replicas. And there is basically a match condition, which I'm just trying to figure this out. Okay, so what this read gives us, it finds the latest version in each one of these replicas, where at least one replica has said that the timestamp is finalized. Finalization happens when you either get fast quorum. After a fast quorum, the coordinator issues are finalized asynchronously, or you in the slow path, you take the replicas take the slow path and send a finalized in response to a finalize message, basically. So you either need a finalized status in one replica, or you at least need f+1 replicas that say that the condition of the key at that target timestamp is tentative. So if you find at least one such value with that timestamp, then you can return that value, basically. Otherwise, you basically have to do this procedure all over again by reducing, by picking a different target, which I quite did not understand, honestly. Okay, moving on. And how does this gossipers work? So basically, at a very high level, gossipers communicate with each one of the servers in its data center and collect the timestamps that they think have been basically written. Once they know that, once they figure out the maximum timestamp that have been written, then they, in each server, then the gossiper basically computes a minimum watermark of all the timestamps from all these servers, and then provides that information to all other gossipers in different data centers. And this exchange happens between all the gossipers across all data centers. And eventually what this gossipers come into conclusion is the minimum timestamp across all data centers, across all servers within those data centers, that can be made visible to the readers, basically. All right, I think I pretty much covered everything. Moving on to failures. The first thing here is basically the coordinator failure. Ocean Vista fixes this by basically using a backup coordinator for performance. So at each region, at each data center, it has two coordinator. One is the primary and the other is the backup. But the point is, if the backup fails, or if either one fails, the other can keep going. But the problem is, if both fails, there are no safety violations, but your progress will stall. The second thing is replica failure. This is dealt, Ocean Vista deals it by electing, using a raft to basically elect a recovery coordinator. So this recovery coordinator ensures that basically does view transfer from a previous view to the next view. And that is all that recovery coordinator serves, basically. A gossiper failure is when a gossiper in a data center fails and they mask it by using multiple gossipers. And when they use multiple gossipers, they made sure to not have any communication between gossipers. So what they have is they have a logic in coordinator where even though multiple gossipers can provide information to the coordinator only picks a timestamp that is the largest, and they are able to do it because the timestamps are always monotonically increasing. So by just having the largest timestamp, they sort of are able to deal with having no communication with gossiper, or even between the gossipers within the same region, basically. However, another failure is the DC failure. So when the whole data center fails, your gossipers all fail. And now the problem is the gossipers in other data centers cannot compute this minimum watermark that can be made visible. So in this case, you basically stall progress, and you need like a membership change protocol to remove this data center from the membership list of all the other gossipers, and then the protocol should proceed again. So in the experiment, the paper tries to answer a couple of questions. The first one is that how much performance you can get basically by having multiple transactions execute in parallel, even when there are conflicts, basically. And the second thing is what is the latency overhead of gossip? And they evaluated it in like three replicas with 3 shards and 3 data centers. And the maximum round trip time between all these data centers between Asia, Europe, and US is about 250 milliseconds. And they use the YCSB benchmark where each transaction read, modified, and wrote 4 keys. They did 2 key distributions. One is the ZipF with coefficient 0.5, and they also used a well-known metric called contention index, where they had 1 hotkey and 3 cold keys. I think this is per client, but I'm not really sure. And they compared with Tapir, basically. Okay, so in this slide, there are 2 figures. On the top, they measure throughput. And even on the bottom, they measure throughput on the left-hand side, but what differs is the right-hand side. So they measure average latency and the commit rate in the bottom plot. So to basically look at the average latency, you have to look at the plot inside the top plot, basically. And you can see that Tapir's latency is actually lower than Ocean Vista's, and this is basically because the gossip and the progression of timestamps on top of gossip takes a much longer time than it does in Tapir. But in contrast, the throughput is much better. They said it's about 10x better when compared to Tapir's throughut. Another benefit of Ocean Vista is that its commit rate remains at 100%. Even when there is contention. That is because of the way they arrange how they execute a transaction. So they do writes first, and then they write the transaction first and with the timestamp, and thereby they use the timestamp to order them. Thereby, they don't have any conflicts per se. Okay, so in order to they observed that Tapir is affected by abort rates, so they decided to do an experiment where there was no aborts for Tapir. Okay, for that they used 1,000 clients for Tapir and a contention index of 0.001, which means that one in every 1,000 requests had basically was hot, basically. So what they did was they had 1,000 hotkeys, and they gave 1 hotkey each to each one of these 1,000 clients. So every client had only 1 hotkey, so which means there were no conflicts in that sense. And there were other also, I think, other cold keys that clients could also access. And this setup is basically called the CI fix in the table below. And for Ocean Vista, they basically use the same distribution, but more clients, because Ocean Vista was able to handle it. That's what they said. But for Tapir, they said they did not add any extra clients, because then the throughput was hurting, basically. Okay, so in the table below, we have Ocean Vista versus, if you compare just Ocean Vista with this key setup compared to the just the CI with 0.001. The speed up within Ocean Vista is about 1x, but for Tapir, if you have no contention, the speed up is 6x. However, when you look at compare between Ocean Vista and Tapir, the speed up, even if you have no contention, is basically 14x, which is the difference might be smaller when compared to 64x in the normal experiments they did, but still the absolute numbers are significant. That's their claim, basically. Yeah, pretty much that's all I have. And thank you.
Cool. Thank you for the very nice presentation.